You ever find yourself reading about some new AI
Yeah.
making these like huge decisions, who gets a loan, what transactions look dodgy, and you just think, okay, but can I actually trust this thing?
Yeah, absolutely.
You want to get a handle on whether these systems are fair, if they're reliable, but
Mm,
honestly, the thought of wading through all the complicated tech jargon, it just feels overwhelming,
totally. And that's exactly what we're tackling today. We're doing a deep dive into how we can measure the trustworthiness of artificial intelligence.
especially in finance, right, where the
Yeah,
stakes are pretty high.
exactly, particularly in finance. And what's really interesting, we've got some new research here that puts forward a whole new framework for thinking about AI risks in this space.
A new frame. Okay. So what's the mission for us today then?
Well, our goal is basically to unpack this new framework, get to the heart of its core ideas, give you a clear understanding of how we can actually assess if these AI systems are reliable.
Kind of the cheat sheet, maybe. Get the key insights without the headache.
Precisely. The shortcut to understanding AI trustworthiness assessment.
Okay, let's dive in then. Why is measuring this risk so critical? I mean, if AI is making finance more efficient, isn't that just good?
Well, it's a fair question. AI and machine learning do bring huge benefits, no doubt. Think
Yeah.
about credit scoring, fraud detection much faster.
All right.
But the problem comes with how many of these models work. They can be like these black boxes.
Black boxes, meaning we put data in, get an answer out, but
Yeah.
the middle part is just murky. We can't really see the logic.
Exactly that. They can be really good at predicting things, but understanding why they made a certain prediction, that can be tough.
Hmm.
And that lack of transparency, plus questions about, are they stable? Are they fair? That's a real worry, especially, like you said, in a tightly regulated area like finance.
Okay, so it's not just about if it works, but how it works and if that how is sound.
Precisely. And you've got regulators pushing for this too. This research actually mentions the EU's AI Act and the US AI Risk Management Framework as major drivers behind needing better ways to measure and manage these AI risks.
So regulation is catching up, demanding more accountability. Makes sense. So what's this proposed solution, this new framework?
Right. So this research introduces something called the Key AI Risk Indicators Framework, KIRI for short.
Kyrie.
Think of KIRI as like a translator. It takes those big regulatory requirements, trustworthy AI, responsible AI, and translates them into practical, measurable principles.
So moving beyond just buzzwords to actual metrics.
Exactly. It's about putting numbers on what trustworthy actually looks like in practice.
Kyrie, I'm guessing it has some core pillars or principles?
It does. It's built around 4 key principles, and they neatly spell out SAFE.
SAFE. Okay, I like that. What does it stand for?
Sustainability, accuracy, fairness, and explainability.
SAFE. Sustainability, accuracy, fairness, explainability.
Got it. And each one tackles a really vital aspect of whether you can actually trust an AI system.
All right, let's break them down. Sustainability. That's not a word I immediately connect with AI or algorithms. What does it mean here?
Yeah, that's a good point. It might sound a bit odd at first, but in the Kyrie context, sustainability is all about resilience.
Resilience, like how tough it is.
Kind of. It's about how stable the AI's results are, especially if it hits, say, extreme market events, weird data, or even cyber attacks. A trustworthy AI shouldn't fall apart when things get unpredictable.
Okay, so robustness, stability,
Hmm.
making sure it doesn't go haywire easily.
Mm.
How do they measure that, especially for those complex black box models?
Well, this is where it gets clever. They suggest adapting methods we already use for simpler models, like regression, where you select the most important variables
Yeah, right.
and applying those ideas to trickier models like random forests or neural networks.
But isn't it harder to tell what's important in those black boxes?
It is. So they propose a step-by-step approach. First, they figure out the importance of each factor using something called Shapley values. We'll definitely circle back to those.
Okay, Shapley values. Factor importance. Then what?
Then they start building simpler versions of the AI, adding the most important factors back in one by one. And crucially, they use statistical tests at each step
Tests for what?
to check if the simpler model performs, statistically just as well as the more complex one it came from. They use tests like Diebold-Mariano or DeLong's test, depending on the type of prediction.
Ah, okay.
If adding more factors doesn't really give a significant boost in performance, they stop.
So the goal is to find the leanest, most stable version of the model that still does the job well, without losing significant accuracy.
Exactly. A simpler model, fewer moving parts, means it's generally more sustainable, less likely to be thrown off by noise or small changes. It helps avoid models that are maybe accurate on paper but brittle in the real world.
That makes a lot of sense. Simpler can be stronger sometimes. Okay, next up in SAFE is A for accuracy. This one sounds more straightforward.
It does. On the surface, accuracy is just comparing the AI's predictions to what actually happened. The loan default was the transaction fraudulent.
Right.
And they use standard statistical measures for this, things like root mean square error for continuous stuff, like predicting a value, and area under the RAC curve, or AURC for categories like yes, no, fraud, not fraud.
Standard performance checks.
Yeah, and again, they use statistical tests like Diebold-Mariano and DeLong's to rigorously compare the accuracy of different models, making sure the differences aren't just chance.
But you mentioned earlier simpler models, the more sustainable ones, might sometimes be less accurate than the super complex ones. Is there a trade-off?
Oh, absolutely. That's a key point. Often, the most complex black box models can squeeze out slightly higher accuracy scores.
Hmm.
Kyer acknowledges this. It's not about demanding the absolute highest accuracy at all costs. It's about finding that balance, a model that's reasonably accurate, but also sustainable, fair, and explainable. You might sacrifice a tiny bit of raw accuracy for a lot more trustworthiness overall.
Okay, finding that balance point. Got it. Now, F for fairness. This is huge, right? All the worries about AI inheriting or even amplifying human biases. How does Kyari tackle fairness?
It's a massive concern, you're right. So within Kyrie, fairness means checking for bias against different groups could be based on gender, ethnicity, location, whatever's relevant, both in the data the AI learns from and in the predictions it makes.
And how do they measure that? Is there a specific test?
They propose something quite innovative here. They adapt a tool called the Gini coefficient.
The Gini coefficient, isn't that usually for, like, income inequality?
Exactly, but they've repurposed it. Instead of income, they use it to measure how concentrated the influence of the AI's key predictive factors is across different population groups.
Oh, okay. How does that work?
So for models where you can see the factors like regression, they look at the variable coefficients. For
Mhm.
black box models, they use those Shapley values again to see how much each factor contributed to the prediction for individuals in different groups. Then the Gini coefficient tells you if the influence of important factors is spread out evenly across groups, that would be a score near 1, indicating fairness. Or if certain factors disproportionately affect specific groups, that's a score closer to 0, suggesting potential bias.
That's really clever. So it's looking under the hood, not just at the final outcome fairness.
Precisely. And they back this up with another statistical test, the Kolmogorov-Smirnov test, to check if the distribution of influence really is significantly uneven across groups. It's a deeper dive into why potential unfairness might be happening.
Okay, that's impressive. Right, last letter in SAFE is E for explainability. We've touched on this with black boxes and Shapley values. Why is this transparency, this explainability, so fundamental for trust?
Well, think about who needs to trust the AI. You've got the data scientists building and tweaking it. They need to understand it to improve it.
Sure.
You've got auditors and regulators who need to verify it's working correctly and compliantly.
Right.
And critically, you have the end users, the customers, who might be affected by its decisions. Why was my loan denied? Why was this transaction flagged? Explainability builds that confidence and allows for meaningful oversight.
And Carey distinguishes between models that are easier to explain and the black boxes you said.
Yes, some models, like your basic regression, are kind of explainable by design. You can see the formula, see how inputs relate to outputs.
Okay.
But for the complex ones, neural networks, random forests, that's where you need techniques like Shapley values to peek inside.
So remind me again, what exactly do Shapley values show us?
Okay, imagine the AI's prediction is like a team payout. The Shapley value tells you the fair contribution of each player, each input feature to that final payout or prediction for one specific instance. It calculates this by considering all the possible ways that feature could have joined the team.
Sounds computationally intensive.
It definitely can be, especially with lots and lots of features, but once you have these values, you can average them across many predictions to get a sense of which features are globally most important in the model.
And then how does Kyrie use this?
Kyrie proposes looking at the percentage of the total explanation power, the sum of all Shapley values that's captured by the key variable selected in that sustainable model we talked about.
Linking it back to sustainability.
Exactly. If a small set of sustainable variables accounts for a large chunk of the Shapley values, the model is considered more explainable. They also suggest using statistical tests, like a t-test, on the Shapley values themselves to check if a variable's explanatory contribution is actually statistically significant.
Okay, wow. SAFE, sustainability, accuracy, fairness, explainability. That's a really comprehensive way to look at it. How does this Kyrie approach actually play out with the different types of AI models used in finance?
Yeah, the research shows how it adapts. For something like regression, it's already quite explainable, right? So you'd focus more on using the Gini coefficient on the variable coefficients for fairness and standard statistical tests for sustainability. Accuracy is measured as usual, but you accept it might be lower than a black box.
Okay. And for the big guns, the random forest, the neural nets, the ones that are often super accurate but opaque?
Right. For those, Shapley values become absolutely critical for both explainability and assessing fairness, using that Gini coefficient on the Shapley values themselves.
Makes sense.
And sustainability, as we discussed, involves that stepwise simplification process, comparing predictive accuracy using tests like DeLong's or Diebold-Mariano to find that simpler, stable model.
So it's like Carrie provides a toolkit, and you pick the right tools depending on the AI model you're examining.
That's a great way to put it. It's flexible.
Now, this research wasn't just theory, was it? I think you mentioned they actually tested this out on real-world financial applications.
They did, and this is where it gets really practical. They included 4 case studies that show Kyrie in action.
Okay, let's hear about them. What was the first one?
First up was credit scoring for small and medium-sized businesses trying to predict the risk of them defaulting on loans. They used a random forest model based on the company's balance sheet data.
Okay, a common finance problem. How did SAFE apply?
So for sustainability, they did that stepwise variable selection using the DeLong's test for accuracy comparison. They found they could create a much simpler model. Interestingly, things like country and industry sector weren't adding much predictive power once key financials were included.
Oh, that's interesting. A potential early hint about fairness, too, maybe.
Exactly. And for accuracy, the random forest performed really well, significantly better than a simpler logistic regression model confirmed by the DeLong's test.
Good. What about fairness across countries?
They used the Gini approach on the Shapley values for key financial variables, comparing across different countries. The results, backed by the Kolmogorov-Smirnov test, showed no significant bias. The key financial drivers seemed to apply fairly regardless of the country.
That's reassuring.
Yeah.
And explainability. Could they tell why the model predicted default?
Yes. Using the average Shapley values, they found that things like return on equity, ROE, profit before tax, leverage, and EBIT were the most influential factors. And together, these top few explained about 90% of the model's Shapley values.
Wow, 90% from just a few key metrics. That's pretty explainable. Okay, solid first case. What was next?
Case number 2 was anti-money laundering, AML. Specifically, monitoring transactions to spot suspicious activity. A classic challenge here is the huge number of false positives you get with traditional systems.
Right, banks get swamped with alerts.
Exactly. So they use AI, a random forest again, on a massive data set from a large bank, over 400 potential features for each transaction.
Whoa, 400 features. Calculating Shapley values for that must have been a lot.
It would have been computationally very heavy. So for sustainability, they actually used a forward stepwise selection based just on predictive accuracy changes using DeLong's test, because running Shapley on all 400 features at each step wasn't practical. They ended up with a model using about 100 variables.
Still quite a few, but much less than 400. How was its accuracy?
Pretty good. The AORC was 0.86, and the F1 score, which balances precision and recall, was 0.79. They also compared it to other models like gradient boosting, XGBoost, and support vector classifiers, SVC. DeLong's test showed it performed similarly to XGBoost, but significantly better than the SVC.
Okay, performs well. What about fairness in the AML context?
Here, they looked at fairness concerning gender. The data set was unbalanced more data for one gender. But even with that imbalance, the Gini measure and KS test on the selected variables suggested they were applied fairly. They also checked the model's accuracy separately for men and women and found similar performance AUROCs of 87% and 85%.
That's good diligence, checking subgroup performance, and explainability for this 100-variable AML model.
They identified the top 5 most important variables using global Shapley values. Things like the customer's overall risk profile, number of active relationships, average transfer amount, the specific transaction amount, and total transfers. These top 5 accounted for about 70% of the model's explainability. They did note, though, that if you only use those five, you'd see a drop in accuracy, highlighting that trade-off again.
Right, the balance between simplicity, explainability, and raw accuracy.
Exactly. And they stress the need for good documentation alongside the model, so internal users and supervisors could understand its workings, even with 100 variables involved.
Makes sense. Okay, two down. What was the third case study?
Third one moved away from direct customer finance and looked at IT systems monitoring within a bank. The goal was to predict IT system failures before they happened to prevent service outages.
Oh, interesting. Using AI for internal operations.
Yeah. They used a model called Light GBM on historical IT incident data. They started with many potential predictors, narrowed them down to 35, and then applied Kyrie.
How does sustainability work here?
They calculated variable importance using Shapley values, then did a stepwise selection, again using statistical tests on the AUROC differences, to arrive at a core set of 17 significant variables.
Okay. And the accuracy of predicting failures.
The AUROC for the selected 17-variable model was about 77%. It had decent recall, meaning it caught a good portion of the actual failures, around 82%, but the precision wasn't super high, around 45%, meaning it still generated a fair number of false alarms.
Okay, so room for improvement perhaps, but catching failures is key. What about fairness for IT systems? What does that even mean?
Good question. Here, the fairness concern was internal. They compared the model's performance on IT systems managed internally by the bank versus systems that were outsourced to third parties.
Ah, okay. Did they find a difference?
They did. The model's predictions were actually more accurate for the internally managed systems. When they dug into why, using the Kolmogorov-Smirnov test on the Shapley values for the errors, they found a significant difference in the distribution of errors between the two types, suggesting it might be a bias in how the model learned differently for the two groups, rather than just a difference in the raw data quality or the nature of failures between internal and outsourced systems. A subtle but important finding about potential model bias.
That is subtle, okay? And explainability for the IT failure prediction.
The Shapley analysis highlighted the most important features, things like the type of application running, performance metrics like APDEX, the number of recent software releases, and system uptime. These key factors explain about 90% of the Shapley values.
Right, so they could pinpoint what the AI was likely keying in on. Okay, one case left, the Parmesan cheese one. Sounds fun.
It is pretty unique. This involved using AI for quality control in cheese making. Specifically, using image analysis, a convolutional neural network, or CNN, to spot anomalies like mold or cracks on Parmesan cheese wheels during their long aging process.
AI cheese inspector. How did Cameri apply to image analysis?
For sustainability, since CNNs have layers and filters, they tested models with increasing complexity, more layers, different filter sizes. They use a DeLong's test to compare the AUROCs, looking for the point where adding complexity didn't significantly improve accuracy. They settled on a model with around 87,000 parameters.
Still sounds like a lot.
It is for a model, but maybe less complex than it could have been. And they had this neat example where a more complex model actually misclassified a rotated image of cheese, while their chosen, slightly simpler, sustainable model got it right.
Huh. Less is more sometimes. What about accuracy overall?
The final model achieved a pretty high AUROC of 85.3%.
Nice. And fairness for cheese, is it unfair to old cheese?
Kind of. They evaluated fairness based on the age of the cheese wheels. They compared the model's accuracy, AUROC, across different age groups. Performance was pretty similar for most age groups, except for the really old cheese, aged over 60 months. For that group, the DeLong test showed a significantly lower accuracy. So yes, you could say the model was slightly unfair in its anomaly prediction for the veteran cheese wheels.
Interesting. Maybe the way anomalies look changes significantly on very old cheese. What about explainability? How do you explain why a CNN flagged a particular spot on a cheese wheel?
Yeah, that's tough with images. Calculating Shapley values for every pixel is usually computationally prohibitive.
So what do they do?
They took a more practical, manual approach. When the AI flagged a wheel, human operators would visually inspect the images, confirm the anomaly, and try to determine its cause, essentially providing the explanation after the fact.
So AI flags it, human explains it, a human-in-the-loop approach for explainability in this case.
Exactly. It shows the principles still apply, even if the measurement technique needs adapting.
Wow, 4 really diverse examples showing Kyrie in action. Okay, let's try and synthesize this. What are the main takeaways for someone trying to understand AI trustworthiness?
I think the biggest takeaway is that this Kyrie framework, built on SAFE, sustainability, accuracy, fairness, and explainability, gives us a much more structured and measurable way to think about AI risk.
Right. It moves beyond just asking, is it accurate?
Exactly. It forces us to consider resilience, bias, transparency, these other critical dimensions of trust, especially in high-stakes areas like finance. It provides concrete ways to assess these aspects.
And the case studies really showed its flexibility, didn't they?
Yeah.
Applying to credit scoring, AML, IT, even cheese quality control,
Yeah.
using different AI models.
Precisely. It's not a rigid one-size-fits-all thing, but a set of principles you can adapt. The research does acknowledge limitations, of course.
Like the computational cost of Shapley values.
Yeah, especially for explainability and fairness in models with tons of features like the AML or image cases. They suggest more research is needed, maybe exploring links between sustainability and explainability to find shortcuts.
So it's a powerful framework, a big step forward, but still evolving as AI itself evolves.
Absolutely. The quest for truly trustworthy AI is definitely ongoing.
Okay, so as we wrap this deep dive up, here's something I want you, the listener, to mull over. We focused heavily on finance today, but think about those SAFE principles: sustainability, accuracy, fairness, explainability.
Mm.
Where else do you see AI making decisions in your life? Healthcare diagnoses, newsfeed algorithms,
Mm.
hiring tools, autonomous vehicles. How relevant are these principles there?
That's a great point.
Could those industries, those applications, benefit from a similarly rigorous way of assessing AI risk? It's definitely food for thought as AI becomes more and more woven into, well, everything. If you want to explore Kyrie further, definitely look up the research on key AI risk indicators. It's a fascinating look into responsible AI development.